Hi guys, okay, so in this video we're going to continue on with chapter 5 and we're going to take a look at section 5.4, Imperfect Real-Time Decisions. So this chapter continues discussion or is talking about basically, we've got this problem where it takes a lot of time to have the AI decide what it's going to do. It takes a lot of resources. So what's another technique we can use to kind of speed that up, right? And so one alternative, one way you can go about speeding things up is just to say, you know what, we'll go ahead and make a decision, and it may not be the perfect one, right? We may not complete the search the entire way. We might kind of fudge things a little bit, and that fudging can speed up the overall search, which can speed up how long it takes for the AI to take its turn to decide on a move, right? So alpha beta pruning, as we saw in section 5.3, can definitely help move things along, speed things up in terms of the AI determining what move it's going to make. But even that can still take too long, depending on how big of a search tree you're going to have. Right, because you're still going all the way to the leaves, or the leaves, I should have said here, of the search tree. Okay, so you're going all the way to the leaves. Yeah, sure, you're pruning some of the subtrees, but for the subtrees that you don't prune, you're still going all the way down to the leaves to evaluate if it's a terminal state, and then if it is, figuring out what the utility value is, and all that kind of stuff, right? So to speed things up even more, to make an improvement upon alpha beta pruning, you just terminate your search early. So essentially this becomes kind of like a depth limited search, right? So terminate your searches early and use an evaluation function that's a heuristic evaluation function. Remember what heuristic means is, take your best guess. Now what this does, or what this will allow us to do, what this function will do, is it'll look at nodes that are not terminal nodes and act as if they were. It'll treat them like they were leaves, right? So, like I said, it's kind of like depth limited search, right? You go down so far in the subtree and then you cut the search off. And if you do that, you don't have to expand all of the child nodes. You don't have to finish searching down the rest of a subtree if you end the search early, and that's going to speed things up because fewer nodes to generate. Okay, so you can modify the MINIMAX or alpha beta by doing what? Right? Replace the utility function with a heuristic function called eval, right? And replace the terminal test function with a cutoff test function. So what's going to happen is that cutoff test function is going to say, all right, is this are we done? Are we're gonna end the search here? Let's cut it off early, guys. Let's pack it up and go home. I know that we could have gone another 20 nodes down the subtree, but we're going to cut it off now. So that cutoff testing function is gonna make that decision. Should we end the test, or should we end the search, excuse me, down this subtree right now? Right? And then if so, then have an evaluation function that evaluates the state at the point of the cutoff. Remember, we're treating that evaluation function is going to treat those non-terminal nodes like they're leaves. They're non-terminal because we cut the search off before we actually went all the way down the subtree. Okay. So what you have is a heuristic MINIMAX function, right? So got state S with a maximum depth of D, so depth limited. We're limiting the depth, right? But the thing is you still have to evaluate the deepest node that you got to when you cut things off, right? You still need some kind of a utility value to be returned from there, right? So what this is showing us is, look, I've got this heuristic MINIMAX function called H dash minimax, pass it a state, pass it a depth limit D, and if the cutoff test, pass it the state, pass it the depth limit, if that returns true, then we're going to go ahead and evaluate the state that we passed to it, right? And then we're going to have to go ahead and find the highest valued action for a group of actions from that state, the lowest valued action from a group of actions of that state. That's what the max and the min over here are doing, right? And remember, we're having the recursion going on, right? We're having the recursion going on. Okay, so recursively calling HMinimax from max's point of view, right? If player S is equal to max, and then we're trying to find the minimum value that's going to be returned by HMinimax if the player is min, right? So find the biggest value if player S, or if the player's turn is max. If max's turn, we want to find the maximum value, right? Of all the possible actions. If it's min's turn, we want to find that minimum value, right? So results doing its thing as usual, generating the new state. That is the result of state S having action A applied to it. And then D, and D plus 1 here, that's basically acting as the counter, right? And once that counter gets to a certain level, cutoff test can evaluate to true, in which case, hey, search is done down that path, so evaluate that state. But you're also passing it a state too, because it could be the case that maybe you actually have reached a leaf. Maybe you have actually reached what is a terminal node, right? And so cutoff test has to be able to detect that too. Okay, now the evaluation function, it's estimating. It's taking a guess of the utility from that state, okay, a guess, because it's not an actual leaf necessarily, right? So it could be the case that you don't have tic-tac-toe 3 in a row. You don't have a cat's eye game, right? So the evaluation function, that eval function, has to look at the state of the board and still come up with some kind of a value for that state, for the algorithm to continue doing its job, right? So it can be easy to see that even if it's not a win, even if it's not a tie, that certain states are better than others, right? If max is the X player and you cut off the search at a state that has 2 in a row for X, right? That's going to be better than a state where when you cut off the search, there was 2 in a row for O, right? So the former is definitely more valuable than the latter, right? So this allows us to have a sort of shortcut, right, where we can terminate the search early down a particular subtree. Not the overall search itself. We're talking about we reach a certain depth limit, like with the depth limited search, and then we evaluate the state at that level using that heuristic evaluation function. Okay, now the evaluation functions, they got to be good, right? They have to be very, very useful. They have to be good guesses as to the value of that state from the point of view of the player doing the searching, right? Because bad ones are going to lose you the game. So for example, max's turn, max is X, okay? 2 X's in a row. If you value that at -1, and you have another state with 2 O's in a row, and you evaluate that at 1, well, it's obvious to see that that's that latter state that's gonna most likely lead to a loss for max, right? So scoring there screwed up, the guessing of the function, the evaluation of the function screwed up. You got to make sure that you keep that all straight and that your evaluation functions are actually giving you useful information. Right, so those terminal states, right, that are going to trigger the cutoff function, it's important that you're ordering them, that you are scoring them in terms of desirability, right? So 2 X's in a row, from Max's point of view, if Max is the X player, it's definitely got to be better than not having any X's in a row, which in turn is going to be better than min, if it's the O player, having multiple O's in a row, right? So the evaluation function definitely needs to be, quote, strongly correlated, unquote, to the chance of winning, right? So a couple of things to keep in mind about this, right? We're not examining everything, right? Some of the states, some of the nodes, they're getting left out, okay, because we're terminating the search early, and that's going to cost us certainty. There's going to be uncertainty as to whether or not the move has been made correctly, or that we're actually making the best move. Not 100% sure, because the AI didn't get a chance to play out the entire game in its head, right? So terminating the search early, we're limiting the depth of the MINIMAX search, right? So can't examine everything. We're going to have some uncertainty introduced in that way. Now, what type of uncertainty are we talking about here, right? It's a form of computational uncertainty, right? It's not random chance here. It's not like we're rolling 2 6-sided dice and we're not sure if we're going to land on Boardwalk or not. It's not like that, right? It's computational uncertainty. It's algorithmic uncertainty. It's uncertainty that's introduced because we've cut our search short. There's no randomness there. There's a definite decision to say, well, we're only going to think 12 moves ahead. We're only going to think 10 moves ahead instead of 50. Okay? So since we didn't examine everything, we got some uncertainty coming in. Right? Now, how do these evaluation functions work? Right? Now, this is actually really kind of interesting to me. You have a state, and the evaluation function is trying to score that state based off of features of the state, right? So what you're thinking about is categories or classes of states that are equivalent, right? So here's an example. You're thinking, well, if I have 1 pawn and my opponent has 2 pawns, well, that's, there's 2 different, that's one situation, but it could be the case that the AI only has 1 pawn no matter what. Now that 1 pawn could be in 64 different positions, okay? But that's one category of states, right? Now it could be the case that the AI has 2 pawns. Okay, fine. Now each category, each broad category, will have some chance of winning, some chance of losing, some chance of drawing, right? So if the AI's got 1 pawn and the human opponent's got 3 pawns, right? There's going to be a certain number of games with that configuration that result in wins, a certain number of games in that configuration that leads to a certain number of losses, and similarly for draws, right? So this evaluation function can figure out the ratio for each of those. So, for example, the black chess player has 1 pawn, the white chess player has 2. So maybe, just for example, that leads to a 72% chance of winning for the AI, 20% chance of losing for the AI, 8% chance of drawing, right? So out of 100 games, 72 are going to lead to a win, 20 are going to lead to a loss, 8 is going to lead to a draw, right? So that ratio can then be used to figure out, well, what's the expected value of that particular state, and then order the states based on that, right? So expected value, 72 times 1 plus 20 times 0 plus 0.08 times 1/2 equals 0.76. So what does that mean here, right? How can we interpret that perspective? Right? Well, 72% chance of a win. So that means that there's a 72% chance of getting that full point. And remember, a win valued at 1 point in the chess example that we've looked at previously. A loss is valued at 0 point from the perspective of the AI, from the perspective of Max. Tie worth a half, right? So 72 wins times 1 point for a win, plus 20 losses times 0 points for a loss, plus 8 draws times half a point. If you add those things up, you get 0.76. That's your expected value for a particular state, right? When you pass that cutoff test and you pass that state that you cut off at, that you got the search off at, to the eval function, it returns, hey, 0.76, right? So what we have is we kind of have this weighted equation here to help you make that guess, right? Because 72% of the time, 72% of the time it's going to be a win, 20% of the time it's going to be a loss, 8% is a draw. So according to this formula, it has an expected value of 0.76, right? So maybe you could say 3/4 of the time we're going to get a win. Maybe that's another way of thinking about it. Okay, so that approach could work for some games, might still be too slow for others, right? So another way of doing it would be figure out values, right? Come up with scores for the contributions from each feature for a particular state. Add those up. That's known as the material value. So example from chess, right? So there's a scoring system that the Chess Federation, whoever puts up the official rules for chess and does all the tournaments, they say that a pawn's worth 1 point, a rook's worth 5, queen's worth 9. Right? So if the AI is, let me give you an example. So AI has got 3 pawns and a rook. Right? So from Max's point of view, that state's worth 8 points. Right? And Min's got a single queen. So that's 9 points for Min, subtract the 2. So you'd say, well, the material value is -1. Right? You can value situations also, but you just add them up to evaluate a position, fine. So mathematically, we're referring to a weighted linear function. Right? That's the term for it. Okay, now, not perfect. There's certain pieces in chess that the further the game goes on, the more powerful they become. So their value is kind of dynamic. So example textbook mentions is, hey, bishops. You got a board that doesn't have a lot of pieces on it. Bishops are relatively more powerful than they were earlier in the game, where there was a lot of clutter in the way. So in that case, you can have non-linear systems, right? So 2 bishops are worth more than 2 knights, right? And then a bishop becomes more valued in the endgame, right? So, as you move forward in the game, the bishops are having their values move up, right? Because, maybe after 20 turns or something, you increase that bishop's value from 5 points to 6, something like that. Okay, based off of the turn number. All right, so cutting off that search. So instead of calling the terminal test function, just the algorithms we look for, or that we've looked at before, instead of using terminal test, use cutoff test, right? So have a line like this in our algorithm. Instead of if terminal test, then return utility, well, if cutoff test, passing the state and the depth, then return the value from the eval function for that particular state. Fine. So what you have to do is you have to choose some kind of a depth that is going to allow you to perform that evaluation of the state within some time limit, right? So you want the AI opponent to take a turn that's only, I don't know, 5 seconds long at the max, right? So you need to do some experimentation. You'd have to say, all right, well, you can go to this certain depth, right? We think that's going to take us the full 5 seconds. That's going to work for us. Okay, fine. Or maybe you can say, well, you can search to a depth of 10. You can think 10 moves ahead, but we also got a clock timer that's ticking. And if the timer runs out before you've reached your depth limit, well, that's it. We're going to go with the move. We're going to go with whatever state happened to be evaluated at that point, or whatever state was the last state that was expanded. All right. So, not perfect. You know, you don't have a guarantee that you're going to get the best move, but you got the best chance for a move, right? So you're going to have counter moves no matter what that min could make to whatever move that max makes, right? So, you know, like, again, not perfect, just gives you the best chance, gives you some kind of an evaluation, the best chance of finding the best move, considering that you're limiting the search, right? You're paying for faster turn times, faster search times at the expense of accuracy. So what's another improvement we can make? We could add a new type of search, a quiescent search, right? That tries to find these special quiescent positions, right? So could be that you've got a state that is really bad down the branch, right? So you can have special cases that say, you know, we're just gonna toss these, right? We're gonna make sure that we don't deal with these. We've hit this particular state as the search goes. Terminate the state right then and there, or excuse me, terminate the search right then and there. Even if we haven't necessarily hit our depth limit, we know there's this particular state that's going to be really freaking bad. So once it pops up, just forget it. You know, there's gonna be a state that's gonna lead us to that really, really, really bad state. As soon as we detect that, we're out. Forget about it. Special case. Okay. All right. So another type of search, or another thing we can do, to speed up our search, forward pruning. Right, let's go ahead and eliminate some particular actions, particular moves. Don't have to worry about it. No further consideration. Forward pruning. Right. So if you think about it, you know, most people are only going to be considering so many chess moves at a time. 3 moves ahead, 4 moves ahead, 8 moves ahead. Fine. Well, you can do a similar kind of thing with respect to the AI. Right. Have the AI only think so many moves ahead. Right? So forward pruning can allow you to eliminate particular moves, particular actions without thinking about it too hard. So one type of forward pruning is the beam search. Okay, so what is this? What are we talking about? Well, for each ply, right? Remember, each ply corresponded to a half turn. You know, white's turn, then black's turn. That's one full ply, half ply for white, half ply for black, right? So look at only a beam of n moves, not all possible moves, right? So don't think about every particular action that the AI could take given a particular state. Just say, all right, well, I'm only going to think about these 3 moves. Instead of, you know, if you got your 8 pawns, instead of saying, well, I'm going to consider what would happen if I moved all 8 pawns. No, just have the AI consider 3 of those pawns. Maybe pick them at random, right? So if I take my turn and I move the first pawn, and I move the 3rd pawn, and I move the 4th pawn, right? Where does the game go from there? Okay, that's kind of what you're thinking about here. You're not considering every possible move every single turn. Only a few. Now, is this bad? Yeah. Can be. Why? There's nothing stopping the best move from getting pruned out of the decision. Right? Now, there's an algorithm that takes this approach that the book doesn't go into too much detail, but it's mentioned just to kind of give you an idea what they're talking about. The prop cut algorithm. So what that does is that uses statistics on previous games. Right? right? So that algorithm is going to draw upon previously played games to do some analysis to determine what moves are probably the safest to cut out, right? So, based off of playing 100 games, moving the first pawn forward 2 squares led to a loss 99% of the time. Well, it's probably safe to ignore that move, right? Anyway, so how this thing generally works: shallow search. Okay, so it doesn't go all the way to all the leaves, and it computes a value v for that, backed up through the recursion tree. The statistics are used, the statistics of a bunch of previous played games, to compute the probability for v at a depth of d. So v is that value, d is the depth, how low into the search or how far into the search you went. So based off of this algorithm, computer scientists, programmers, whatever, they were able to build an AI for Othello that beat traditional algorithms, the other types of algorithms we studied so far, most of the time. Okay, now, bunch of different techniques went into more detail, more depth with some than others, but combining all of them together, researchers were able to put together a chess game that could look at up to 10 plies in reasonable time, up to 10 moves. I go, white goes, black goes, 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 10 total of that. Okay, so reasonable time. Could have a computer do that in reasonable time. Now, 10 plies, looking ahead, 10 plies, that's at an expert chess player's level. Now, if you tune this even further, researchers were able to tune this even further, and they could get an AI that could play at grandmaster level. Okay, now that additional tuning required the use of some special tables, or that tuning included using special tables. Okay, so we'll talk about that a little bit. So search versus lookup, right? Now, for the opening move, okay, it can be, for playing chess or for playing checkers, whatever game, the first move, oftentimes it's overkill to generate an entire tree just for that one move. Now in chess, this stuff's been studied to death, right? And people who know these things, people who study these things, have identified what all the good opening moves are, right? And they've also identified what all of the best endings, say the last 3 moves, are, right? There's only so many combinations of opening moves and ending moves that you can take. Some are demonstrably better than others. So instead of generating an entire search tree to determine what that first move should be, you already know through history, through studying how games, and through mathematics, what the best moves are. This has been played out. People know. They've done the research on it. So instead of generating an entire search tree, just do a lookup on a table, right? If I'm the black chess player and the white chess player moves a pawn a certain position, or they open with their knight moving somewhere, right? There is a best move or a better move to take than others in response as the black player. So take the state that the game's in after white made that opening move, and then do a lookup in a table, maybe a hash table or something, to find the best counter move for that opening move, right? So you don't have to generate the whole tree. That goes way faster, right? Big O of 1, right? If you're using a hash table, you have a constant lookup, boom, right? So much faster. So table, the solution, very good for the best 10 moves, right? These have been studied by humans, been studied to death. This is known information. Okay. Now, for Endgame, computer is definitely better of thinking about all the possible combinations really quickly, right? So last 3 moves, last 5 moves, right? The computer can outthink a human here much better. Okay, so human being trying to figure out that checkmate can take a long time to figure that out. Computer's going to beat the human hands down. Okay, so what the computer can do for closing out the game is computing what textbook refers to as a policy. So what that is hey, let's map every possible state at the end of the game to the best move in that state. Then all you have to do, look up, right? Do a lookup for that move. You don't have to recompute it over and over and over again. Again, the table is coming back into play. Okay, so consider KBNK. I guess that's what they say in chess circles, right? King, bishop, knight, king. So you got this scenario. It's at the end of the game. You got a king, you got a bishop, you got a knight, and you got a king. Okay, so you're trying to close out the game. So here's some numbers for you, right? There's 462 different combinations if you want to put 2 kings on the board that are not adjacent to each other in this scenario, right? Thinking about the possible states that could happen. That would leave 62 possible squares left for the bishop, 61 possible for the knight, and then 2 squares for each player to move next. So add all that up, 462 times 62 times 62 times 2, right? That's going to equal 3.4 million possible combinations. Some are checkmates, some are not. I put the checkmates in a table. From that table, you can do a search, right? You can do a retrograde search. And what does that mean? A search through all the moves in reverse. Okay, so look at all those possibilities. Eventually, you will get a set of moves that's going to be a guaranteed win. Right? So this is the scenario. This image right here is the scenario that we're talking about. So there's going to be a certain number of combinations. You can map those combinations to a particular move. Right? What move here? Checkmates. Put those in a table. Do a lookup on the table. Speeds things up immensely. Okay, so that's the end of section 5.4. And the biggest thing here, just to summarize what this section is, look, you don't have to generate an entire search tree, right? Alpha beta pruning allowed us to eliminate entire subtrees from the search. Might not be enough. The search still might take too long. So what can you do? Limit the depth of the search, right? Only go so far into the search before you cut it off, right? Don't go all the way to the actual leaves. Treat a node along the path between the root and the actual leaves as a leaf, right? So that's going to require that you have a cutoff test function that identifies when the search should terminate down a particular subtree, and then a heuristic evaluation function that can then accurately, or as accurately as possible, make a guess as to the value of that cutoff state, right? And then, you know, we looked at a couple different ways of doing that, of evaluating features of that state to help inform the AI as to the next move that it's going to take, right? So basically those are just modifications to the MINIMAX algorithm, right? Replacing the terminal test function with the cutoff test function, replacing the utility function with the eval function. Okay, and then you can speed it up even more with the use of tables, right? And so we talked about, you know, tables for opening moves and then mapping combinations of moves that lead to checkmates and putting that in a table for endgame. Alright, so that's the end of section 5.4. Next video we'll talk about stochastic games, which has to do with introducing randomness in the games, like die rolls for like Monopoly, rolling the 2d6, or backgammon, rolling those 2d6, and how does the AI work with that.